Hello and welcome to today's video. Again, we'll be talking about game theory today. You'll remember that we have recently introduced matrix games as a special case of the bimatrix games. We also termed those zero-sum games, and you remember that a matrix game or a zero-sum game means that whatever one player loses, the other gains. So the sum of payoffs is always zero. The goal of that reduction was to find an easier way to compute Nash equilibria or optimal strategies for the players. And we're going to start this journey today. Today we're going to look at how to compute optimal strategies for zero-sum games. So today's section is titled Optimal Strategies for Matrix Games. And as I said, the task of today's section is to find the best possible strategies for each individual player. Before we start that, I'd like to introduce a quick notation, or at least remind you of that. Remember this notation here, a 1 like this, that stands for the all ones vector. So that's a vector with only ones of suitable length. And in particular, we'll use that to denote the sets of strategies SC and SR for the column and row player. Remember, those were all the strategies that a player has available, all vectors in R to the N usually for the column player and R to the M for the row player. And the condition on those vectors are all entries are between 0 and 1, and the sum of all entries is equal to 1. And we can express this sum is equal to 1 nicely by saying the matrix product of this all ones vector and the vector x is equal to 1. And then, of course, we also want that all entries are non-negative. We don't need to enforce less or equal to 1 for the entries, because that will be automatic. If there's only non-negative entries and they sum up to 1, then of course no entry can be higher than 1. So that's not a problem. And we'll use that notation, this especially here, we'll use that extensively from now on. So just write it down once. What that means is basically the sum of the xi's, I from 1 to n. Now let's have a look at the task of finding optimal strategies. Basically what that means is we have a couple of optimization problems to solve. We want to find an optimal strategy. And let's first consider the column player for that task. So if the column player chooses some strategy, then of course the row player, if he would know that strategy, would be able to find the best response. And as the column player and row player both know everything about that game, of course, the column player would be able to anticipate what the row player does. So let's see how this would work out. Let's say column plays a fixed strategy X star. That's a strategy in SC. Then Rao would determine his best response. And to do so, he'd solve an optimization problem. And what he would do is, well, the payoff that we get in the end would be y transposed a x star. Remember, column plays x star always. And Rao has to choose a suitable y vector. And that would be the payoff that Rao gets for a certain y vector. And Rao wants to minimize that payoff, because with our convention, the payoff is what Rao has to pay. So he would minimize overall y in SR. So that's the payoff that we would get. Now, of course, Column can also solve that optimization problem. So Column knows that for a certain strategy X star, this is the payoff that Column would get. Column wants to maximize the payoff. So she needs to find a strategy, an X star, that has a minimum for the Rao player that is as high as possible. So again, this is the payoff the Rao player would determine given that strategy X star. But now the Column player can choose an X star such that this minimum is maximized. So that's what Column wants to do. So the Column player needs to determine a strategy X star in SC that maximizes this minimum. So here's Column's optimization problem. And that problem is called a maxi-min problem. We'll see in a second why. So what Column needs to do is he needs to find a strategy X with X in the set of available strategies SC that maximizes the minimum of y transposed AX, where y is chosen over SR. So to say, for every X that the Column player can choose, the Rao player will choose a corresponding y that minimizes the payoff for that given X. And now the Column player wants to find a strategy X that maximizes those minimum. So that's the maxi-min problem that the Column player faces. Now let's have a look at the Rao player. Things are similar for the Rao player. The Rao player can fix a strategy Y star, and then Column's best response would of course be to maximize the payoff given that Y star. So similarly, if Rao plays a fixed strategy Y star in SR, then Column will choose a strategy X in SC that maximizes the payoff. So what we will get is the maximum of y star transposed ax, x in SC. And now Rao knows this. So for any given Rao strategy, Rao knows what the column player will do. So Rao will choose the strategy that minimizes this maximum. And that leads to Rao's optimization problem, and that is now a minimax problem. So what Rao wants to do is he wants to minimize over all strategies y in SR the maximum of y transposed AX taken over all X in SC. So those are the different optimization problems that those players face. Now it doesn't seem very easy to solve these, but of course it would at least be nice if the results were compatible with each other, right? So let's say we solve one problem. Let's say we solve the problem from Rao's point of view. We solve Rao's minimax problem. Then we get an optimal strategy for Rao. Now if you use that strategy and feed it back to the column player, then the column player will also choose the corresponding strategy, an X, that maximizes then the inner expression, this here. So we have a pair of strategies. Of course, it would be nice if we got the same pair of strategies if we use this expression here. And that is indeed the case. That's one of the central theorems of game theory, the theorem by von Neumann. And that theorem will also give us an idea of how we could compute those optimal strategies. So let's write down that theorem first. So all that says is, consider a matrix game. That matrix game is specified by the payoff matrix as usual. A, and we'll have that be an M by N matrix. Then the following holds. First, it doesn't matter whether we solve the minimax problem or the max-min problem, the result will always be the same. So the maximum of the minimum of y transposed AX, where the minimum is taken over all y in SR, and the maximum is taken over all X in SC, that is the same as the minimum over all y in SR of the maximum over X in SC of y transposed AX. So both problems give us equal results in terms of the payoff. We will not necessarily get the same strategies because there might be different strategies or different strategy pairs that yield the same payoff. But that doesn't really matter. Both of these strategies pair, or all of these strategy pairs would then be perfectly fine solutions as long as the payoff is the same. And the theorem tells us the payoff will always be the same no matter which of the two problems you actually solve. Second, of course, it's important to know that actually there is a solution to these optimization problems. And that's the second point of that theorem. that says the game admits a pair of optimal strategies. We call those strategies X star, Y star, and they are in SC and SR. That are optimal for both the minimax and the maximum problem. And now those strategies are called optimal strategies. Third, there is a very close connection between optimal strategies and Nash equilibria, and that connection is they're the same. So any Nash equilibrium also constitutes a pair of optimal strategies and vice versa. So a pair X star, Y star in SC times SR is optimal if and only if it constitutes a Nash equilibrium. That is not surprising. If you have a pair of optimal strategies, of course, no one will want to deviate from that. And if no one wants to deviate from a pair of strategies, well, they should better be optimal. Otherwise, at least one of the players would have a better choice. And remember, optimal means individually optimal. Yeah? That does not mean there might not be a better choice, even a better choice for all players. But in the situation, the individual rational best choice is this optimal strategy. Part 4. Now, the question of how to compute such an optimal strategy is still open, and that is settled by part 4. And that says a pair of strategies X star, Y star, again in SC times SR, is optimal if and only if X star and Y star are optimal solutions to the following linear programming problems. And you've hopefully seen linear programming problems already. You should be familiar with those from management science. So I'll just write down the 2 linear programs that we need to solve here. The first is we maximize a value that we call nu, subject to the condition a times x minus nu times the all once vector is greater or equal to 0, and subject to the conditions 1 transpose x is equal to 1 and x is greater or equal to 0 component wise. And on the other hand, for y we have a minimization problem. We minimize nu under the condition y transposed a minus mu times 1 transposed is less or equal to 0. 1 transpose y is equal to 1, and y is greater or equal to 0. Now let's take a quick minute to explain those linear programming problems here. What happens here? Obviously, these last two conditions here, those should be clear. That says the sum of the x entries is 1 and the x entries are positive, so that means x is a valid strategy for the column player. We have the same thing here. Y is a valid strategy for the row player. Now what this condition here means, right? What this says is AX is at least nu times the all ones vector. So each row of AX is greater or equal to nu. But what does that mean? Remember, this AX is part of the payoff that we get. The payoff is this expression here, y transposed AX. So if each row of AX is greater or equal to nu, then what this here do? Y transposed times this vector AX, that's the linear combination of the rows of AX. Remember, AX is just a column vector. So each row of AX is greater or equal to nu, and then we do a linear combination with, remember that the y is a strategy vector, so that only has non-negative components. And that means the result will of course always be greater or equal to nu, because also the entries of y sum up to 1. Non-negative components sum up to 1, and we only have entries that are greater or equal to nu, then this sum will necessarily also be greater or equal to nu. So what that means is the column player selects some strategy X that guarantees that the row player cannot enforce a payoff that is less than nu. So nu is the least the row player will get. And of course, he wants to maximize that payoff nu. So nu is going to be the payoff of the column player. So what that means is no matter what row plays, the payoff y transposed AX will always be greater to y transposed 1 times nu, and that will be greater or equal to nu. Okay, so that means we get at least a payoff of nu, and then this is maximized because the column player wants to maximize payoff. On the other hand, if you look at this expression here, what this says is y transposed A is less or equal to mu times 1 transposed. So that's the left part of the payoff, right? This is the payoff here. This is the y transposed A part. And what that means is, well, we have a row that has entries that are less or equal to mu, so whatever the column player does based on that will always yield a total payoff less or equal to nu. So with the same argument, no matter what the column player does, the payoff y transposed AX will be less or equal to mu times 1 transposed X, which is mu. So we get at most a payoff of mu, and of course the row player wants to minimize that payoff. So that's the objective function here. Okay, so that nu and mu, that would be the payoff of the respective player. And that's what these linear programs do. And of course, You also know that from management science, I trust. For an optimal solution, those two payoffs, nu and mu, those will be the same. You'll hopefully notice that basically these two linear programming problems are duals to each other. So in an optimum, the outcome will be the same. So for an optimal solution of both LPs, we have nu equals mu. And as a quick side note, more or less, this payoff, which is then both, apart from the sign for both players, the payoff is a characteristic of a matrix game, and that payoff is called the value of the game. So that's a definition. For a matrix game specified by the payoff matrix A in R to the m by n, the value of, well, this is the minimum over the maxima of y transpose AX, maximizing over X in SC, minimizing over Y in SR. And of course, as you know, you could also have taken the max-min problem instead of minimax. It doesn't matter. So that value is called the value of the game. So what that is basically is the expected payoff if both players play their optimal strategies, if both players behave rationally. And second part of the game, second part of the definition, a game is called fair if the value is 0. So the intuition behind that is, of course, a game with a value of 0 means there's an expected payoff of 0. So if the game is played multiple times, then the column player will win sometimes, the row player will win sometimes. There might be different payoffs, but in the long run, it should all even out. So that's what we would call a fair game. On the other hand, if the value is positive, that means in the long run, the column player will gain something. And that means the game is biased in favor of the column player. If the value is negative, then in the long run, the row player would gain something. And that means the game is biased in favor of the row player. Now, please do not confuse that value with the notion of a zero-sum game. The value is only defined for zero-sum games. So all the games, all the matrix games that we're looking at are zero-sum games, meaning the column player gets exactly what the row player pays and vice versa. That does not yet tell us anything about biasness. For example, if you set up a game where, regardless of the outcome, the row player always pays €1 to the column player, that's a zero-sum game. Because the payment of one player equals the gain of the other player in every possible outcome. Always zero-sum. But of course, that game is heavily biased. One player always wins, the other never. So that wouldn't have a value of 0, but it would still be a zero-sum game. So please do not confuse these two notions. Okay, let's make a quick note about that. What that means is a positive value, so a positive expected payoff, would mean the game is biased in favor of column. And on the other hand, a negative value would mean the game is biased in favor of row. Okay, so now we do have an instrument, a way of actually computing optimal strategies. It will require us to solve linear programming problems, but you do know how to solve those, so that shouldn't be much of a problem for you. It's quite a hassle sometimes. That's correct. Yeah, but there is an algorithm that does the work, and we can apply that. Although it might be some work to do it, but from a mathematical point of view, we'd say the problem is solved. There is an easy algorithm that can be easily implemented, and that can be solved. Let's see a quick example of how that might be solved. And again, we'll use the game of parity. For example, we already know the Nash equilibrium for parity, so let's see if our new method yields the same result. You will remember that parity is defined by this matrix here. So that's our payoff matrix. And now we want optimal strategies. So what do? Well, we take a look at the LP problems. So first problem is we want to maximize the payoff for the column player, maximize mu, such that a times x is greater or equal to nu. So a times x means we have x1 minus x2 is greater or equal to nu, and minus x1 plus x2 is greater or equal to nu as well. And then we also have x1 plus x2 is 1, and x is greater or equal to 0, component-wise. And on the other hand, we have the minimization problem of the row player. Our player wants to minimize mu, such that y transposed times a is less or equal to mu times 1 transposed. So y transposed, y times a is equal to, let's see, so we have y1 minus y2. That needs to be less or equal to mu, and we get minus y1 plus y2 less or equal to mu. So those are the two conditions. And then again, of course, we need to have the sum of the two equal to 1, and we need all entries to be greater or equal to 0. So what does that mean? Well, in particular, we get the two conditions out of that one. Let's say x1 minus x2 needs to be greater or equal to nu, and this other condition here, if we multiply that by minus 1, then we get x1 minus x2 is less or equal to minus mu. So altogether, this yields mu is less or equal to x1 minus x2 is less or equal to minus mu. So, well, how does that help? What we have here is basically an inequality on the mu's. So mu is less or equal to minus mu. Or 2 mu is less or equal to 0. Or mu is less or equal to 0. And now we want to maximize mu. in this specific problem. So that means the best possible mu that we can still get would be 0. So any solution with mu equals 0 is surely optimal. And now let's see if we can find a solution with mu equals 0. Before we do that, let's do the same analysis for the other problem here. For the right problem, this one here. With the same argument, here we can say y1 minus y2 is less or equal to mu. And again, we multiply this second inequality by minus 1. And we get y1 minus y2 is greater or equal to minus mu. And that yields minus mu is less or equal to y1 minus y2. That's the second inequality. And that by the first inequality is less or equal to mu. So altogether what we have is minus mu is less or equal to mu, or 2 mu is greater or equal to 0, or simply mu is greater or equal to 0. Now we minimize. Mu is surely greater or equal to 0 if we have a feasible solution. So the best we could get is equal to 0. And that means, in this case, any solution with mu equal to 0 is optimal. And again, let's see if we can find a solution that has this property. Remember, we have these inequalities here. Or rather, these inequalities. If you look back at the original, and now if we substitute 0 for nu and for mu, what we get are the inequalities x1 minus x2 is greater or equal to 0, and minus x1 plus x2 is also greater or equal to 0. And here we get y1 minus y2 is less or equal to 0, and minus y1 plus y2 is less or equal to 0. Now let's try and plug those together. If we first look at this here and this here, what that tells us is x1 is greater or equal to x2. And for the y's, it says y1 is less or equal to y2. So we got this here from the orange inequality. Now let's have a look at this inequality. We can solve those for x2 and for y2. And doing so says, well, for the green x inequality, we get x2 is greater or equal to x1. So we can continue this chain of inequalities here by this green inequality. And for the y's, we can do the same thing. y2 is less or equal to y1. So again, let's continue this chain by the green inequality. And what that gives us is a very simple solution, actually. So if x1 is greater or equal to x2, which is then greater or equal to x1, that means x1 and x2 must be equal. Otherwise, that could never hold. So that means x1 is equal to x2. And of course, for the y's, we have the same conclusion. y1 is equal to y2. We also know that x1 and x2 sum up to 1 and are non-negative, and the same holds for the y's. So the only solution where this can hold is x1 and x2 must both be 1 over 2. And same here, y1 and y2 must both be 1 over 2. So we found the solutions to the LP problems. And that means we found our optimal strategies. And those are X star and Y star, both the same optimal strategies, and the strategy is 1 over 2, 1 over 2, or 1/2 times 1, 1. And the value of the game is nu and mu. They have the same value, of course, so the value is 0. That means that game is a fair game. And this outcome confirms the result we have about the Nash equilibrium. We already determined the Nash equilibrium of parity. That was also 1 over 2, 1 over 2 for both strategies. So the optimal strategies are the same in this case. And I've seen we've solved the LPs doing some clever manipulation with the inequalities here. That made things a little easier and shorter, but of course that cannot always be done. So you need to be aware that sometimes you will have to use the simplex algorithm, especially if the games get more complicated, more complex. Then there's probably no easy way around the simplex algorithm anymore. I just didn't want to spend the time of doing 2 complete simplex runs here in this video, but you're welcome to try this at home. See if you can apply the simplex algorithm to these 2 optimization problems, and your results should hopefully be the same that we got in this analysis. So this completes this video on optimal strategies for matrix games, and I hope I'll see you in one of the next videos on game theory.